Welcome back to Chem 131A. Where we last left our hero, we had decided that it was possible for a light particle to tunnel through a forbidden region, much like a high jumper, going over a bar, but not going over it, just appearing on the other side, collecting the trophy, without having enough energy to actually go over, a phenomenon that we call tunneling, to indicate that we went through, but we did not go over. Today, what we're going to talk about is we're going to talk about tunneling microscopy, and that's an application that turns out to be very, very interesting for a lot of reasons. And then we're going to introduce a little more complex problem on vibrations. The reason why vibrations are a more complex problem is that the potential energy for a vibrational problem is not a square well or something that's mathematically so easy. It's trickier because we get x squared in there, and we're going to see how we have to handle that. It certainly seems at first blush that this phenomenon of quantum mechanical tunneling is just a small niche field for experts and people in ivory towers to study. But just like a lot of basic research, it oftentimes leads to killer applications. And this is very, very true in this case. We saw, for example, that the phenomenon that when you measure something, you cause it to change, allowed us to do quantum cryptography so that we could have this key that we could tell if somebody was spying on us, and we could establish an unbreakable code between us. Likewise, this phenomenon of tunneling, because when the barrier is big, it depends exponentially on the distance, and that means it's very sensitive to it in some sense. That means that something that's close tends to dominate everything, and that lets us have a trick to make a very sharp looking point. And one of these applications then of tunneling is called scanning tunneling, the scanning tunneling microscope, or the STM, sometimes called scanning probe. It was Gerd Binnig and Heinrich Rohrer when they were working at IBM. They were granted a patent on the scanning tunneling microscope in 1982 while they were at IBM, and I've given you a reference here on Google. They have a list basically of all the patents that have ever been granted. They're public knowledge. You can search them, you can find out, and boy, are there a lot of them. And this patent was 4,343,993, and that was back in 1982. If you take a sharpened metal tip, and I mean really sharp as you can make it, but as we'll see, it may not matter how sharp you make it, because when you look closely, it's going to be extremely sharp no matter what, if you're fairly lucky. And you bring it up to a clean surface, like a gold surface, and you put a voltage on the tip. Then there's nothing between the tip and the surface except a vacuum. And the way we interpret that is that the electron can't come off from the gold atom too far, because its energy its potential is getting too high as it goes away from the atom. The atom has a big positive nuclear charge that's pulling the atom down, that's holding it down. And therefore, crossing through this region of space is like jumping through that region V in our tunneling problem. Classically, it should not happen. We need to have a conductor to have a current with electrons. But if the electron's a wave, then if we get near the surface of the gold or something else, then the fact that the wave function can sneak out a little bit means if it can sneak into the tip, then there's some chance that the electron materializes in the tip. And that gives us a current. And this current is going to be some noisy thing because it occurs because of tunneling, but it's going to be a current, and it's going to depend, if we move the tip closer, it's going to get much, much bigger because as the barrier gets thinner, the tunneling gets exponentially more likely. And what that means is that the position of this tip floating over this surface is extremely sensitive to the distance. How can you use that to do something? Well, this is not a microscope in the conventional sense of a light microscope where you might look at a hair or look at cells. This is only for looking at the topography of a surface, but it can be fantastic because you can put pieces of DNA on a surface or something like that, and you can use variants, the atomic force microscope, for example, to look at these things and see all kinds of things. The amount of current that you get is a measure of the local density of states. In other words, it has to do with how many electrons can be there and how their wave functions are on the surface, and the distance of the tip to the actual surface itself. And this works with a conducting surface. If we raster the tip over the surface by moving it back and forth, and we keep track of where we are with a little system of piezoelectrics that's just like a GPS for your car, it knows exactly where the thing is, then what we can do is, if the current gets too big, we assume we're too close to the surface and we pull the tip up. And we try to keep the current at a certain value. And what we keep track of as a function of the value of the current, trying to keep it locked on to a certain value that's convenient, that means we're close enough to get something. We know we aren't too far away, we aren't getting anything. But we're far enough away that we can move reasonably. The problem is if we're too close and we come along with the tip and there's a mesa or something on the surface and we come along, then it'll increase, but then we'll crash the tip into the surface, and then we put a notch in the surface, sort of like scratching an LP in the old days if you were careless, and we may change the tip because the tip has atoms on it and they may get knocked off and they get knocked around. We have to strike a compromise. We want to get a current that we can tell that we're in contact. We aren't actually touching, but we're in tunneling contact with the surface. But we don't want it to be so high that if we move too quickly that we're likely to crash the tip. In the early days of doing these experiments, people crashed the tip into the surface all the time. Now there are commercial kinds of machines that even people have made STMs on their own. Avid hobbyists, you can actually make this device, so it's not so difficult to make. Because of the exponential dependence then, let's just imagine the tip. The tip, whatever it is, has been sharpened. It's very sharp. It's as sharp as you can make a sharp thing. And why do you want it to be so sharp? Because you want to be able to see little egg carton things of atoms and things on the surface. And so your tip should be very sharp. If your tip is this big wide thing, then you kind of blur everything together and you can't see anything. But it turns out, because of the exponential dependence, if there's a cluster of grapes hanging off the tip of atoms that are piled up there, and it could be anywhere, it doesn't have to be in the middle of the tip, but whatever's closest, all the current is going to go through there. And so that's perfect because it means that you just get lucky with the tip and then all the current goes through there, and the tip sort of makes itself sharper by the way the current depends on the proximity. And so unless you're very unlucky, unlucky would be two tips coming down two bunches of grapes, both the same size, that would give you a very confusing image. That doesn't happen very likely. The other ones contribute exponentially less current, and that means that they don't bother you much. You can experiment with different tips, and people did a lot of that, until you find a good one. And then you conduct experiments with this good tip. You try to get your Ph.D. with it if you can, until you're unlucky and you're too aggressive or something and you crash the tip into the surface. And of course, most of the time when you're looking at things with the STM, you're looking at things that you kind of assume are pretty smooth. You're trying to look at details of a flat surface of atoms. You're trying to see, for example, if you have a material, whether some of the atoms might, if you have two different kinds of atoms, some of the atoms might like to be on the surface of the material in a different amount than in the bulk. And you can see that kind of behavior with this. And you can also use the STM to do chemical reactions. If you have a surface of some molecules and you bring down your tip and now you can influence, you've got current going through, what you can do is you can do a pulse, sort of like having a meteor come in and hit, and you can make a small chemical reaction at that point, and you can write a little dot there, for example, and then you can move the tip and pulse it again, and you can modify the surface by doing this over and over, and there was interest in that at one point. Here's a figure from the patent. You can see back in 1982, you drew things by hand. And you drew a lot of things by hand. In fact, you used something called a Leroy set back then to get the numbers to look nice and so forth, and you drew them in India ink. This is from the original scan of the original document. Here they're showing this tip. They're showing a flat surface. They're showing Z, which is the up and down. They're showing X and Y, which they're controlling with these piezoelectric controllers. They're showing a plot of what they get, and they're showing a screen which is going to show the topography, what the current did as a function of Z. And here's a figure 3 from the same patent. What you can see here is that they're showing the current as a function of the distance from the tip from the surface, and they're drawing an exponential, which is exactly what we derive for tunneling, and they're showing that the current should go like e to the minus something, and then you can see that there's a distance in the exponential. That's the exponential distance dependence that we derived for a very unlikely event, and you want this to be unlikely, you don't want it to be too likely. And here is a schematic, again, figure 4 from their patent. There's a surface, there's a tip. The tip is very near the surface. The tip has some shape, and all the current is coming from the part of the tip that's closest to the surface. So that part of the tip is a super sharp part that's giving all the current, and the other part is giving a little current, which is kind of a noisy background, but it's not a big deal. And then you're going to move the tip along, and you're going to keep the current constant, and by keeping track of how you have to adjust the height of the tip to keep the current constant, you get a picture of the lay of the land. The tip can also be used to actually pick up atoms and move them around. And here's a spectacular example of that, which Don Eigler published in Nature in 1990. And again, working at IBM, here you have a very, very flat atomic precision nickel surface. And on it are scattered some xenon atoms. Xenon atoms have a lot of electron density, and they show up there as these round things, just like you might imagine a xenon atom should look. And you can see in frame A, they're all randomly positioned. And what they were able to do is first use the microscope to see where everything is. Be quite careful. And then go to an exact position where you know there is an atom. And of course, this has to be extremely cold. So this is basically at liquid helium temperature, because if this is at room temperature, or even liquid nitrogen temperature, it's going to be like drops of water on a fry pan. They'll be moving all over the place, and it won't matter that you scan through and see where they are, because the next time you come through, they're going to be somewhere else, and half the time they'll just pop off the surface entirely. There won't be enough sticking for them to stay on. So this is extremely, extremely cold, which is also a challenge, because you have to cool your microscope, you have to cool the surface, you have to cool everything down, you have to be extremely careful. And then you come down with the tip on top. You know it's still there because it's so cold, and you actually push on it, and then you drag it somewhere. And with your XY magical GPS system there, you park it, and then you go get another atom, and you drag it, and another one, and you drag it, and then in between times, you then image the surface very gently, so that you are not dragging any atoms, and then you can see your progress. And what they show here is they can write out IBM in xenon atoms on a nickel surface using the STM. And this was really just a spectacular example of how you can manipulate the very smallest things with such exquisite detail using this device. Unfortunately, I think nobody has figured out how to use the device to make extremely small things like computer chips or other things that might be ultra miniaturized, because it's too slow, it takes too long, and it has limited ability to make any kind of 3D shapes. Here's another image. This is from a group at Carnegie Mellon in the physics department. And what this is this is a picture of the surface of silicon. And the 111 just means that it's a certain crystal plane. So if I take silicon, it has a certain crystalline structure. I can cut at certain angles, just like cutting a diamond. And I cut at certain angles, and I would expect to have certain kinds of atomic patterns. But what tends to happen once I cut is that the atoms are very unhappy if they're sticking out too far. They're very unhappy because they don't have enough bonding neighbors, so-called dangling bonds, bonds that are going out into space, doing nothing. And what they may decide to do if they're unhappy enough, it's sort of like a lonely person going to a bar, they may pull in and try to make extra bonds with other atoms, which has nothing to do with the original structure that you would expect, and that's called reconstruction. And here you can see this so-called 5x5 reconstruction of silicon. And you can even see there's one defect in the middle of the picture where there's an atom that's kind of dislocated, that's out of position. But most of them seem very perfect, so it's very interesting. Of course, the color here is false. The color here is just to guide the eye. All right, now let's go on to vibrations. Vibrations are important because when we do a chemical reaction, we take a chemical bond and we usually break it. We break it and we make a new bond. And the whole business of chemistry is to take stuff where things are organized. They're the same atoms, but they're worthless, just junk, manure. And then we make and break bonds, little witchcraft, and out comes some very, very important antibiotic, which is worth a lot more money. And in order to understand how that works in detail, we need to have a very good idea of how strong the bonds are. We We need to be able to predict if we're going to make something, if it's going to have strong bonds or weak bonds. And we need to understand also if it's going to absorb light so that we can do an assay to see if we've made what we think we've made, like IR spectroscopy. Here what I've shown is a potential energy curve for the hydrogen molecule, H2, the simplest molecule. The proton-proton distance is along the x-axis in picometers, and the energy, the electronic energy, so we calculate this curve by moving the protons together at different distances. And then we freeze them, even though we know they can't be frozen by the uncertainty principle, and we calculate the electronic energy. And if the protons are too close, they tend to repel each other, plus the electrons, the orbitals are too close together, it's not optimum. If they're at the right distance, then the electrons can be in between. Each proton sees both electrons as part of the principle of bonding, as we'll see, is that they share. Each proton, each hydrogen thinks it's a helium atom, and that's a very stable configuration. And then, as we tend to pull the protons apart, the electron clouds can't overlap. This proton cannot see anything to do with this electron. And so the strength of interaction decreases, and finally when they're far apart, they're just two hydrogen atoms. And that's shown then in this so-called potential energy curve, which is just the electronic energy plotted as a function of the frozen distance of the two protons. When they're too close, you see that the electronic energy is above zero. That means that when they're that close, that they're more unstable than just two hydrogen atoms apart. But there is a well. There is a position where the two hydrogen atoms working together are much more stable than two hydrogen atoms apart, and that's the stable H2 molecule. And then the potential curve goes back to zero as they go back toward just two isolated hydrogen atoms. Now, near the bottom of the well, at the equilibrium distance, which was 74 picometers in that previous figure, the potential has a minimum. And where the potential has a minimum, calculus tells us that the slope must be zero. And that means that if we expand the potential, V of r, that curve, whatever the form of it is, in a Taylor series, which we do by taking the function value and then the derivative, the second derivative, so on, around the equilibrium position, we can write V of r is equal to V of Re, which is the equilibrium, the lowest point, plus r minus Re. So again, a trick of rearranging something by making it seem more complicated. And we can write that as V of Re plus delta r, where delta r is how much the bond is stretched or compressed from the equilibrium. What we get is, in the Taylor series, we get V of r evaluated at Re, which we'll just call V of Re, plus the derivative of V of r evaluated at Re times delta r, plus 1 over 2 factorial times the second derivative of V of r evaluated at Re times delta r squared, plus blah, blah, blah. Keeps on going. Same pattern. If we look at the bottom of the well, the derivative is 0. And therefore, it simplifies quite a bit. Near the bottom of the well, the derivative is 0 right there. So we throw that term away because we evaluate that term right at r equals Re. If we're near the bottom of the well, then r is close to Re. So what we will assume then is that r minus Re squared is something, but r minus Re cubed and all the higher ones are too small because r is very close to Re, and so therefore they're much smaller. And if we do that, we end up with this following very simple form for the potential, which is what we're going to use when we do the Schrödinger equation, because we don't want to use the real potential or we'll never get out alive. It'll be far too difficult for us to do. We get V of Re plus 1/2 k times r minus re quantity squared, where k is the second derivative of v with respect to r, evaluated at r equals re. And k here is the force constant, not the, so I apologize for using k again, but k is conventionally the force constant of the spring, and before k was the wave vector e to the ikx. This is a different k, and there's another k, Boltzmann's constant, which you may put k sub b to try to keep that one separate, but we'll use k when we talk about vibrations to mean the force constant of a spring. And for small displacements, then we have that the motion should be harmonic unless k is 0. If k happens to be 0, then that term goes away, and then the whole motion is described by something very funny, whichever terms are left over. But usually k is not 0 because the thing comes down and goes back up, and so it has some part of it that's quadratic, and around the bottom that's going to be the main part of the actual potential. Therefore, we can model a chemical bond as a one-dimensional harmonic oscillator. We totally ignore any kinds of other displacements or in other directions or anything funny, and we just say, look, these are two things on a line here. There's a distance between them. We know the energy. What we want to figure out is what's the wave function as a function of this distance between them, given the form of the potential energy. We can always adjust the energy 0, so we can call the bottom of the well 0, even though it's not, even though for hydrogen it's minus 4.5 eV down. We can call it 0, and then we can just add it later if we want to get the real energy. So we don't have to worry about that in the math, and so we'll call it 0 when the displacement is 0. And just to keep in keeping with what we've been done for consistency, rather than using r minus re, I'll just introduce a variable x, and psi will be a function of x. And so if x is 0, then they're at the equilibrium, and if x is something else, plus or minus, then it's away from equilibrium. We get the same tired old time independent Schrödinger equation to solve. Minus h bar squared over 2m d squared psi dx squared, now plus 1/2 kx squared psi is equal to e psi. And given k and m, our task is to figure out what the allowed values of E are and what the functional form of psi is. For the particle in the box, the allowed values of E went like n squared, and psi was a sine wave. Now we've got a different potential completely. It's got this x squared, so it keeps continuously changing. So we could guess it's going to be quite a bit harder to do it, and that would be a very good guess, as we'll see. If we have the two nuclei connected together, let me just remark that the mass m here is the mass, the reduced mass of the oscillator, or m1 m2 over m1 plus m2. But we won't worry. For what we're doing, we just want to get a qualitative feel. So we'll just keep m, and m is some mass associated with the oscillator. Now, before we solve the differential equation, it's a good idea to take a second and try to figure out what it is we would predict that we should see. That way, if we get something ridiculous because we make a mistake, we'll know it. So the question is, what properties should the wave function have? And that's pretty easy to suss out. First, the energy will be quantized. Why? Because the potential is going like that, and something that's going like that is tending to confine the particle. The particle cannot just go anywhere because the potential gets bigger and bigger and bigger and bigger, so it's got to be trapped. If it's trapped, It's got to be quantized. It's got to go way out there, and the energy, it has to fit into the space, and therefore it's going to be quantized. We don't know what shape it's going to have. Secondly, the lowest energy eigenstate can't be zero energy. It wasn't zero energy for the particle in a box either. The problem with that is if we picked zero there, it went away, and we have a similar problem here. If we want to have a real wave function, it's going to have to be in there. It's going to have to satisfy the uncertainty principle, and therefore it's going to have non-zero p squared, and it has non-zero x squared because it's not an infinitely narrow box, and therefore it's going to have non-zero energy. And thirdly, the wave function has to die away somehow as x gets far from zero. The reason why there is that the potential keeps getting larger, and also it has to die away to zero because it has to be normalizable. And finally, the ground state should have no nodes. And the reason for that is that we, by analogy with the particle in a box, when we did the particle in a box, it was zero at the edge because it had to be, but it wasn't zero anywhere in between. It was just a lump. And if we change this to this, we expect this lump to change, but we don't expect it to change into two lumps. Therefore, we expect something like a turtle in there somehow, sitting there. Not very exciting, but just sitting there. And if we have an excited state, if there are excited states in this potential, we would expect them to have nodes just like the higher excited states of the particle in a box. But, well, how should we solve the differential equation? Remember, I said the most powerful method to solve differential equations is often guessing, and I'm going to try to guess. I have something times the derivative of the wave function twice plus some other stuff is equal to the wave function times a number. I've got to get the other stuff to go away. Therefore, I need to have a function that generates itself again. That's so I can get this part. And I need it to generate a little other garbage times itself so that I can get rid of the 1/2 kx squared, which I want to go away because there's no 1/2 kx squared on the right-hand side. And I couldn't use just e to the x to do that because e to the x will give itself times a number. But I could use e to the something else, and I would expect that I'm going to have to use an exponential function because they're always the solutions of these differential equations. Furthermore, I could guess that, look, this thing has symmetry. If I draw the potential at the bottom, x is 0, and then it's going up, and it's symmetrical. And therefore, the wave function has to be symmetrical too. And that means that we can't have anything like e to the minus alpha x or something like that because that's not symmetrical around 0. We could have that plus e to the plus alpha x, but we can see right away that neither of those would be any good. Since those don't look good, you try the next power up. And if you try the next power up, which is a Gaussian function, you get very lucky. And in fact, it seems to work. So let's guess. Let's guess psi of x is equal to a times the exponential function of minus a times x squared, little a. Big A is the normalization constant. We won't worry about what that is at this time. And little a is something that we're going to have to pick to make it work. And we'll see what the condition is. You wouldn't necessarily know that this would work, but you can easily work it out. So let's go ahead and work it out. If we want to take the second derivative and multiply by h bar squared over 2m. The first derivative of that function is that function again times the derivative. Remember that the derivative of e to the u is e to the u du dx. We have minus ax squared as u. The derivative of that is minus 2ax. So the first derivative is a times exponential minus ax squared times minus 2ax, that whole thing. The second derivative, now we've got a product of two things. We've got the derivative of u times v, and that is the derivative of u times v plus the derivative of v times u. And the first one, we've done the derivative before, so therefore the derivative, the second derivative is capital A e to the minus ax squared times minus 2a plus a times e to the minus x squared times minus 2ax times minus 2ax again. The first 2ax comes from du dx. The second minus 2ax comes from the fact that that second one is there. And we can then put these together, and we see that we got what we want. We got a times e to the minus ax squared, so that gave the same thing reproduced. And then we have this term, and it has two parts. It has a 4a squared x squared, which if we pick a right, is going to cancel out the 1/2 kx squared. And then it's got the other part, 2a, which is going to have something to do with the energy. Let's have a look. If we put everything in then into the Schrödinger equation, we come to the following conclusion. Minus h bar squared over 2m, capital A e to the minus ax squared times 4a squared x squared minus 2a plus 1/2 k squared, again capital A e to the minus ax squared, is equal to e times the same thing. And so now we can divide both sides by capital A e to the minus ax squared and get a relationship between little a and k. If we want those terms to cancel, because there's no x squared term on the right hand side, it's just e. The terms in x squared cancel. That means that minus h bar squared over 2m times 4a squared x squared plus 1/2 kx squared is equal to 0. And for that to be equal to 0 for all values of x, a, little a, has to equal to the square root of mk upon 2h bar. And a, therefore, the exponential argument, has to do with the mass and the spring constant and Planck's constant. And boy, is that sweet, because this is quantum mechanics, and that's exactly the kind of behavior that we would have expected to see. And we can make a connection with a classical oscillator. If you've done the classical oscillator, if you haven't, then you should. But the angular frequency of the classical oscillator, what's the angular frequency? Well, if I see this thing going back and forth like that, I can interpret it as something, as a projection of something going around. Because if something's going around, it's going like this. And that angular frequency is the square root of k over m. And since omega, the angular frequency, is the square root of k over m, the square root of mk is equal to m times omega. And using that, we can now figure out the energy. The energy is minus h bar squared over 2m times minus 2a. That's the only part that's left over, because the x is gone by our choice of a. And that's h bar squared over m, square root of 2mk over 2h, and that's h bar over 2m times m omega. The m's cancel, and we get h bar omega over 2. That is the ground state energy of the oscillator, which is not 0. The oscillator is always a little bit excited. It can't be 0 because of the uncertainty principle. And we can make a connection between what we found with light by saying, look, omega, the angular frequency, is 2 pi nu is the regular frequency. So h bar omega over 2 is also equal to h nu over 2. And h nu was the quantization of a photon. So this is similar to the quantization of light, except that now there's a factor of 2 in the denominator for the energy. But other than that, it's very closely related. Knowing the value of A now, little a, then we can calculate and normalize the entire wave function and determine the value of big A, because now we know how wide this Gaussian function is, we know what area it's going to have when we integrate it, and so we know how big this big A has to be to make the probability of finding the displacement somewhere equal to unity. And our normalization condition now is that we should take the square integral of this thing from minus infinity to infinity as usual, and the integral of e to the minus 2ax squared dx, that's a standard integral which you can look up. That's the square root of pi over 2 divided by the square root of a, and capital A squared times that should be equal to 1. And therefore, if we take the square root of both sides, we find that a squared should be 2a divided by pi to the 1/4 power, and that's capital A. We've picked A as usual to have real phase, because we always like A having real phase. We're just biased toward that. Just as we did with the particle in a box wave functions, we had that 2IA, and we said, well, we'll get rid of the I because it doesn't matter. This, therefore, gives us our very final form for the ground state of the harmonic oscillator. And that is 2a over pi to the 1/4 e to the minus ax squared, and then I can put in all the things with m and omega for a, and I get this very nice formula. Now, the problem with this approach of guessing is that whatever you don't guess doesn't turn up. And we guessed one thing and we found one thing, and it made sense. Why? Because it's a Gaussian, it's like a big turtle. It has no nodes. It has a low energy, which satisfies the uncertainty principle, but it doesn't have any more energy than that. But now what we would have to do is we would have to try to guess some higher thing. It's not like the particle in a box where we had n pi. We don't have any n yet here in this problem. We just have this one wave function and this one solution. We suspect, and we're right, that because it's like a particle in a box, just slightly different, that there should be a ladder of states. And in fact, the ladder is actually equally spaced at n plus 1/2 times h bar omega, which makes this potential really unique because it's the only form where you get an equally spaced ladder of states all the way up to infinity. And there are some very, very nice mathematical ways of attacking that problem that are very beautiful, but they take us a little bit too far afield for our course, and they don't have that much to do with chemistry. They have more to do with operator algebra and quantum physics than chemistry. And so we're not going to explore those, but we'll just quote that the general solution is some polynomial in x that you have to pick carefully times e to the minus ax squared. So that part of it is always the same. Now, what is the interpretation of this? It's completely different than a classical oscillator, because the classical oscillator has the highest probability. If we take a film of it, it goes out, it stretches, it stops, it turns around, come back through, that's where x is 0, that's where it's perfect, compresses, stops, back through again, and so on. And the chance of finding it, if it's oscillating right at the equilibrium position, is not likely. If you just grab it at some point and measure its distance apart, it's much more likely to be either fully stretched, because it has to turn around there, that's why it's called the turning point, or fully compressed. But when we look at the ground state of the harmonic oscillator, what we find is something completely different. The highest chance is that the thing is in the middle, in the perfect position, where it shouldn't be. So it seems as if it's trying to stay in the middle, but it's actually spreading out a little bit, not because it wants to, but because it has to, because of the uncertainty principle. And therefore, this ground state of the harmonic oscillator looks completely different than a classical oscillator. And that caused a lot of consternation, I think, in the very early days, because it looked so different. And how do you interpret this thing? You want to make sure you haven't made a mistake, or something's not right in the equations. But it turns out this agrees exactly with what we observe. And there are many experiments where we take a molecule and we excite an electron, and it really looks like it comes mostly from the equilibrium position. We very rarely find something coming from a extended position. So this interpretation of this is correct. Like I said, the oscillator can't sit still. It's like a small kid. It has to squirm around to satisfy the uncertainty principle, and the 0-point energy depends on the square root of the spring constant K and on the inverse square root of the mass. And this gives rise to something called the isotope effect. Let's have a look at the isotope effect. Suppose we have two isotopes. For example, hydrogen has a single proton. Deuterium is a single proton plus a neutron. It's heavier, but the charge is the same. And deuterium behaves much the same way as hydrogen does. There's D2O. You can use it to make NMR samples, for example. The neutrons don't have any charge, no electric charge. So the electrons don't really care too much about the neutrons. And therefore, what we expect to a first approximation is that the force constant, which has to do with the electronic orbitals, and the repulsion of the two protons doesn't depend on whether they're two protons or two deuterons. It depends on the charge and the separation. And the electrons pretty much don't care. There are small effects because the electron's sneaky, it can see the neutron. So there's some small effects, but basically the form of the potential energy surface is the same. But what's different then is the mass. And therefore this whole field of isotope effects is a great field to get into if you're interested in theoretical effects of 0-point energy and tunneling and all these subtle things, because you have a perfect thing where everything's the same except the mass, and so your calculation even doesn't have to be quite so good, because even the things that in your calculation that are slightly wrong are the same except for the mass. And so unless you're very unlucky, you get a pretty good result anyway. If we have then a CD bond, a carbon-deuterium bond, versus a carbon-hydrogen bond, the carbon-deuterium bond is stronger, because it in the sense that the amount of energy it takes to go from the ground vibrational state, which is as close to the bottom of the well as you can get, to where the bond is broken, which is the same place on the curve, is higher for the CD. And then we'll close with this. Here's how it might look. On the left, we have a molecule that could either have a hydrogen or a deuterium, and let's say it's carbon. And then in the chemical reaction, this bond breaks, and as it's breaking, the force constant gets less. So in the transition state, it's almost off, and therefore the potential is very wide, because the force constant for something that is a weak bond is not a very stiff spring. But when it is actually the reactant, it is stiff. And therefore there's a big difference when it's the reactant, and there's a small difference when it's the transition state. And that then translates into a different rate of reaction. That means that if we have molecules that could be CD or CH, and we react them somehow, we expect the CH ones to react more quickly than the CD ones. And this is called the kinetic isotope effect. And I've adapted this little figure here from Wikipedia to just show how this works. In fact, this again seems like a very esoteric thing, but you would be amazed if you go to the enzymology literature and you look, how do I know if this enzyme is breaking this bond or that bond, or what is the rate limiting step for the synthesis of cholesterol or the removal of something from the body? You put in a deuterium as a spy and you look for the deuterated product versus the protonated product, and boy, do you find a ton of information. So this is now translated all the way from this esoteric effect of the harmonic oscillator, the uncertainty principle, and zero-point energy, all the way to modern medicine, where it's used to figure out what's going on in the body. Next time we'll continue on with some of these one-dimensional model problems, and then we'll begin to actually do some multi-dimensional quantum mechanical problems. I'll close it there.